Welcome back. In this lecture, we begin a discussion on Sobolev spaces. So, whatever we discuss about these spaces in the next few classes, so those topics will be used in the second part of this course very frequently and extensively. And if you are listening for the first time about this subject, so you have to really work hard to grasp the basics of this. Again, this is a very vast subject, so will not be able to do many things, but will concentrate on those things which are required in the second part of this course. So again, let me begin. So it's a repetition. So, but again with this Dirichlet integral. So you have already seen that. So this is a bit motivation for the study of these spaces. So it's analogous to the development of Lebesgue integration theory starting from continuous functions. As we already seen, if we equip the space of continuous functions, say on an interval, with integral norm, then that space will not be complete, and completeness is an important requirement in all our studies. So similarly, so now let me state here this. So let me write infimum, though it's so this integral, this is the Dirichlet integral. Okay. So without even bringing in the Lebesgue integration, so let's try to understand this in the classical sense. So here omega is a bounded region. Region means connected and open. So in fact, this is going to be standing hypothesis later in Rn. Okay. And infimum, so we have to mention where infimum is taken. Infimum is taken over all u. So first of all, we want this integral to be finite, so let's put this C1 omega bar. So this space, and more generally Cm omega bar, this is space of all continuous functions, differentiable functions up to first order here, in generally mth order in omega, which can be extended continuously up to omega bar. Okay, so that's the this space, and then you equip that with the sup norm. That's fine, but here we are using the integral. Okay, to make it non-trivial. Okay, so for example, if I include constant function, then this integral will be 0. Certainly infimum is 0 and it's attained by any constant. Okay, so let's avoid that. To avoid that, so I put this additional condition. Equal to 1. Again, this can be a constant. So you just, since we are dealing with smooth functions, so I put u equal to 0 on the boundary. Sorry. Equal to 0 Okay. So, now these conditions make it a non-trivial problem. So, constants are avoided, and so again the main difficulty here is the minimizing sequence may not converge in this norm. Okay, so we are not shown that that's a norm, but okay, just let me in the norm. So I'll put a colon there, this del u square over omega. So even let me put this. Okay, so that's the main difficulty. Okay, that we have already seen even in the case of continuous functions with an integral norm. Okay, so in analogy with that, so Sobolev spaces can be thought of completion of this space with certain integral norms. Okay, that will eventually come to that point, but in so probably you will see an answer to this infimum of this Dirichlet integral in the second part of the course, but here is a simple thing you can do. So in one dimension, so let me just mention, if you are aware of that thing, that is fine. Okay, so let me just the case of n equal to 1, and let me take omega to be some interval 0 1 for example. Okay, so just take C1 this interval, and the Dirichlet integral in this case is 0 to 1 u prime x square dx. Okay, so we have to minimize r. Okay, let me write that minimization problem. Okay, so again same condition. So on the boundary u is 0, so we are putting that condition, and integral 0 to 1 u square is 1. Okay. So there is a an inequality called Wertinger's inequality. Let me quickly mention that. Okay. So if u is a C1 function and vanishing on 0 1, then it says this integral 0 to 1 u square is less than or equal to some constant 0 to 1 u prime square. Okay. In higher dimensions, this is called Poincare inequality, which we are going to derive, but this is so far some constant C positive. Okay. So without bothering about the best possible constant, so using this condition u 0 equal to u 1 equal to 0, you can easily derive this nice inequality. Okay. Obviously this is not true for any C1 function. For example, if I take just a constant, then non-zero constant, so the left hand side will be some positive number and right hand side is 0. So this vanishing on the boundary u 0 equal to u 1 equal to 0 is essential for this inequality. Okay. And in this case, a solution to the minimization problem. So if you have not seen it, you can a solution for the or the only solutions. Okay, so that's solution for the minimization problem. So, I am going to write the minimizer itself. So, there are two solutions. So, they differ only in sign. So, let me just write that root 2 sine pi x, x is in 0 1. So, with this thing, so this constant is chosen so that the integral u square is 1, okay, so it vanishes on the boundary, and when you put in this thing you will see that whatever this, if you evaluate, you will get the minimum value. Okay, so minimum value is something like 1 by pi square r. Okay. So this comes in the calculus of variation problem. It's one dimensional, so it's you get an ODE which you can solve. So you can write it, this minimization problem, as a global minimization problem with some Lagrange multiplier, and that's where this minimum comes, and you also get the minimizer. Okay, so with this brief introduction, let me now define definition of Sobolev space. Okay, so again omega in Rn is open. Okay, so for the definition we don't need any restrictions on the domain. Okay, so this WMP, okay, this is standard notation. Okay, so this is definition. So this is set of all u in LP omega. Okay, so this again for the definition you can include infinity, and m is a non-negative integer. Okay, such that d alpha of u also in LP omega for alpha less than or equal to m. Okay, and these are distributional derivatives. Okay, so that's being LP function, certainly it has distributional derivative of any order. Okay, and the requirement is that so those distributional derivative is also in LP omega. So here we use a shorter name for this. We also call this weak derivative, because here we are going to use only in the integral sense. Okay, so we are going to call it weak derivative. Okay, so m, this integer denotes the number of derivatives, weak derivatives, and p denotes the power of integration, LP. Okay, so this when p is equal to 2, that's what we are going to restrict. It's very customary to denote this WMP omega or WM2. Okay, let me write. omega by Hm. These are standard notations you find in the literature. Okay. The advantage of working with p equal to 2 is that this becomes a Hilbert space. Okay. So, let me write more generally norm in WMP omega. Okay. So, if u is in WMP, so we just write MP. Okay. So, this is, so since all derivatives up to order m are in LP, so I just write LP omega here, because there will be too many indices, so let us not confuse with that. So, take the power here p and you take the sum over all multi indices up to order m and then you take. So, these are necessary to make it triangle inequality work. Okay. So, of course, you can also give several equivalent norms. So, that's not a problem. Okay. So, this with this thing, so if p is not equal to 2, WMP is a Banach space. So, of course, this needs you have to work, but it is not difficult, because we already know that Cauchy sequences in LP space, they converge to some LP function. So, use that and you get that this is a Banach space, and when p equal to 2, so now I use that Hm omega is a Hilbert space. Okay. So, this so let me write. So, if UV in Hm omega, the inner product okay, is UV. So, let me write in full thing. So, this is just summation d alpha u d alpha v in L2 omega. So, this is inner product in L2 omega, and you just take the sum overall. Okay. So, in this way we can borrow all the properties of Banach spaces or Hilbert spaces, as the case may be, in order to study this special class of Sobolev spaces. Okay. So, let me just stress one point here, okay, because that is important. So, I just said this distributional derivative. So, just remember this is always the case. Okay. So, let me hereafter assume that p equal to 2, p equal to 2. So, we work only in Hm omega, and let me also assume that omega is a bounded region. So, essentially we use this boundedness for the integrability of constant functions. So, many times we want to integrate that. So, that is okay. Of course, you should see where it is not required. So, some results may go through without boundedness. Okay. So, that weak derivative. So, let me stress that, because that is an important point. Otherwise, the tendency will be to treat these functions also as smooth functions, and that is not true. Okay. So, if u belongs to Hm omega, then so that I am going to just write the weak derivative part. So, this u d alpha phi, this is omega. Okay. So, sometimes I am, when that omega is fixed, so I need not even write omega here. Or phi for all phi in d omega. Okay. So, that is C infinity functions with compact support in omega, and d alpha u is in L to omega. Okay. So, this d alpha u, this weak derivative, gets a connection to u only through this relation. This is important. Okay. You do not have a point-wise definition of d alpha u as it is. Okay. You may get later. Okay. But as of now, just from the definition of the Sobolev space, this d alpha of u, its relation to u comes only from this relation. So, that is important to remember. Otherwise, that we get the tendency that this is just usual derivative. Okay. So, if you want, you can write this as g alpha, and then you call it g alpha equal to d alpha u. Okay. So, that is very important. Okay. So, one of the important observation, so that we before going further, okay, so just want to make a comment on this thing. Okay. So, in the definition of the weak derivative or distributional derivative, we use C infinity functions with compact support. So, that is first remark. Okay. So, let me call it this as star may use phi only finitely many in star, and this observation is required for future purposes. We want to multiply the functions in Hm omega by some smooth functions of finite order, not infinite order. So, how do you observe quickly? Okay. There are two ways of seeing this. Okay. So, one thing is if star holds for, so I am just explain it in words. So, if star holds for all phi Cm functions with compact support, certainly it holds for C infinity functions with compact support. And conversely, if star holds for C infinity functions, and then you, for any Cm function, you use its mollifiers. Okay. So, that is one argument. Okay. So, one argument is use mollifiers to see that this is valid. So, if it is valid for Cm functions, so we can use mollifiers to get for any Cm C infinity function. So, that is one observation. And another observation, quickly, it comes from again theory of distributions. So, since these are functions, they are distributions of finite order. Okay, so that, so if T is a distribution of finite order, say n, then T extends as a linear continuous linear functional to this Cn C omega. So that is, recall the notation. So T can be thought of dn omega prime. Okay, so that's and since these are distributions of finite order, so we can treat them as linear functionals on dn for some finite n. So here it is order m, so we can just use only up to order m. So we need not take, that's not required. Okay. So in particular, if we take h1, so just continuously differential functions with compact support will do. Okay. So that's an important observation. And next thing, so already we have seen examples of locally integral functions having derivatives not in the class of functions. So they are already measures. Okay. So obviously there is something special about such requirement. So what are those requirements? Okay. So when we can have the weak solution also in the class of integrable functions. Okay. So that makes this species special and those functions also special. Okay. So let me just state two results. So many of the results are, I am not going to prove for the reason they are proofs, some proofs are very lengthy, simple but lengthy, and some are easily observed. Okay. So that's okay. So here is the first result in this direction. So let me just state it as a theorem. Okay. Suppose f in L2 omega has compact support, so extend f by 0 outside its support. Okay. If 1 is less than k less than n and h not 0, okay. So define. So these are finite differences, h k 1 by h f of x plus h e k minus. So E1, E2, En are standard unit vectors in Rn. Okay, so this is f. Okay, so if f is in L2, so this is just difference of two L2 functions. So each del h k f is also an L2 function. Okay. So here are the so two things. Just want to then A if del f by del x k. So, let me not repeat that. So, this is weak derivative. Okay. L to omega, then del h k f L to omega is less than or equal to del f by del x k L to omega, and more importantly this del h k f minus del f by del x k L to omega tends to 0 as h tends to 0. Okay. So, the requirement that the weak derivative is in L2 imposes conditions on the these finite differences. So, conversely, if del h k f L to omega is bounded for all h. So, this c does not depend on h. Okay. Then del f by del x k exists and in L2, of course, exists always in distribution sense in L2, and let me just say that this one holds. Of course, this is quite cumbersome to deal with the finite differences if you want to go for higher order derivatives. Okay. So, let me again state one more theorem. Okay. Just so, here we can deal with all the derivatives in one go. Okay. So, just let me state that. So, this uses the mollifiers. They are also called averaging functions. Okay. So, just so let me just state this as a theorem. So, for f in L to omega to have weak derivative d alpha. So, here we are dealing with derivative of any order. So, alpha is a multi-index. It is necessary and sufficient. So, that for all omega tilde open and whose closure is also in omega. So, since we are assuming omega is bounded, so omega tilde bar is compact. There exist constants. So, this depends on only the that compact set, compact subset, and again epsilon, again this epsilon 0, this again positive such that d alpha f epsilon L2 omega tilde is bounded for all okay. So, this f epsilon is mollifier. So, let me again just recall that f star rho epsilon, okay, that is convolution. Okay. So, these f epsilons are all C infinity functions. So, this is just the classical derivative, but to require that integrability condition. Okay. So, with that I will just stop here and we will continue discussion on the Sobolev spaces in the next class. Thank you.